Okay, so now that we've learned the definition of the dot product or scalar product, let's just look at two quick examples. And let me just say before we do this example, or these examples, one, vector product, dot product, scalar product, any kind of product of vectors, you still have to have units. The units of the dot product or scalar product between any two vectors is the units of one vector times the units of another vector. I mention that because this example that I took from the book that we're going to do is sort of a generic example where the vectors don't have units. I want to emphasize that any time we're taking a dot product or scalar product, the end result is going to be a number plus units. So as a reminder, we have two different ways of calculating the dot product of two vectors. So if I have vector A dotted into vector B, so the dot product or the scalar product, two different ways of calculating it. One, it's the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. That's useful if you have the magnitude of each vector and the angle between them. Or it's also given by the x component of A times the x component of B plus the y component of A times the y component of B plus, there is no C, plus the z component of A times the z component of B. So let's take a look at example problem 915. Evaluate the dot product of the three pairs of vectors in the figure below. So one, good to keep in mind, anytime the angle between the vectors is between 0 and 90, that dot product is going to be positive. Anytime the angle is 90 degrees, the dot product is going to be 0. And anytime the angle is between 90 and 180, the dot product is going to be negative. So let's first look at A. So here's a case where we're given the magnitude of each vector and the angle between it. So we're going to use this definition of the dot product. Okay, so what we have is vector A has a magnitude of 3, vector B has a magnitude of 5, the angle between them is 40 degrees. So A dot B is just going to be the magnitude of A, which is 3, times the magnitude of B, which is 5, times the cosine of the angle between them, which in this case is 40 degrees. Break out handy calculator, 15 times cosine of 40. What we get is 11.5. And again, another weird thing here is they're giving you the magnitudes in just one significant figure. So this is actually 11.49. If we were to do this to one significant figure, we would write this as 1 times 10 to the 2. But let's just assume two significant figures for these problems. So B, I want the dot product of C dot D. So the magnitude of C is 2. The magnitude of D is 3. The angle between the two vectors is 140 degrees. So I take 2 times 3 times the cosine of 140. And what I get is negative 4.6. And again, there should be units, but this is just a generic problem. So a little hint, anytime the two vectors are perpendicular to each other, you don't even need to go and do the work because cosine of 90 is 0. But again, just to be clear, if I want the dot product of E dot F, it's going to be the magnitude of E, which is 3, times the magnitude of F, which is 4, times the cosine of the angle between them, which in this case is 90 degrees. What we get is 0. So if you're calculating the dot product or scalar product, and you have the magnitude of each vector and the angle between them, it's just magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. Now let's look at what happens if we are given the x and y components. So if you're given the x and y components, then the easiest thing to do is to use the definition, well, not the definition, but to use this version of calculating the dot product. Multiply the x components together, multiply the y components together, multiply the z components together, and then add them all up. So again, for this example, this is 911. It says evaluate the dot product, a little small, a dot b, if, and you've got two different vectors. So again, in this case, we're going to get the dot product by multiplying the x components together the y components together and the z components together. So again, as a reminder, ax bx plus ay by plus az bz. So for a, the dot product of a dot b, I take the x component of a, which is 4, times the x component of b, which is -2, and then I add the y component of a, which is -2, times the y component of b, which is -3, and then they don't have z components. So what I have is 8 times negative, or 4 times -2, which is -8, plus -2 times -3, which is 6. So we get -8 plus 6. My dot product is -2. And again, there really should be units on this. B. Again, if I'm doing a dot b, it is the x component of a, which is 4, times the x component of b, which is 2, plus the y component of a, which is 2, times the y component of b, which is 3. So in this case, what I get is 8 plus 6. My dot product is 14. Pretty straightforward. Enjoy it now, because once we get to chapter 12, we'll start looking at the cross product or vector product, which is much more challenging, much more interesting, but we're not going to do that until chapter 12. So that's it. Scalar or dot product, pretty easy. 2 ways of calculating the dot product between any 2 vectors. The first one is if you're given the magnitude of each vector and the angle between them. It's just the magnitude of A times the magnitude of B times the cosine of the angle between them. If instead you're given A and B in terms of x, y, and z components, then it's ax bx plus ay by plus az bz. The 2 are equivalent. That's it. Stay tuned. Thursday, we will officially start chapter 9 by looking at this energy model, conservation of energy, lots and lots of great stuff. So please, please, please take the time when you're at home and read ahead. The more you can read ahead before I lecture on the material, especially given how we're doing it, the better it's going to be for you. All right, good luck, stay healthy, and I hope to see you guys in person sometime in the not too distant future. All right, take care.